In this video we look at the FP1 work on matrices. We're expected to be familiar with the basic arithmetic of matrices, the idea of identity matrices and determinant of matrices and inverses of matrices for both 2x2 matrices and 3x3 matrices. Know that two matrices are equal only if they have the same number of rows, the same number of columns, and the corresponding elements of each matrix are the same. And we need to know that the transpose of a matrix is simply a new matrix obtained from the original matrix by saying that the first row of the original matrix becomes the first column of the new matrix, the second row of the original matrix is the second column of the new matrix, and so on. We need to be familiar with the basic arithmetic operations of matrices. We need to be familiar with the identity matrix for 2x2 matrices and 3x3 matrices. And then we need to be confident and familiar with the idea of determinant of a matrix, of a 2x2 matrix, and that if the determinant is non-zero, then an inverse matrix exists, and that if the determinant is zero, then A does not have an inverse, and that A is called a singular matrix. And then there are similar ideas that we need to be familiar with for the 3x3 matrices. And finally, we need to know that we can use inverse matrices when dealing with equations involving matrices. So for the first one, we have a matrix given, and the very first thing we are asked to do is to calculate A squared. So A squared is simply A multiplied by itself, so that's 1, 2, 3, 4 times by 1, 2, 3, 4. So the first entry is going to be 1 times 1 plus 2 times 3, which is 7. The entry here is going to be 1 times 2 plus 2 times 4, so that's 2 plus 8, which is 10. Entry down here is going to be 3 times 1 plus 4 times 3, which is 15. And then the final entry, we've got 3 times 2 plus 4 times 4, so that's 6 plus 16, which is 22. And we're being asked to show that that's the same thing as 5a plus 2i. So 5a plus 2i is 5 times 1, 2, 3, 4 plus 2 times the identity matrix. So that is 5, 10, 15, 20 plus 2, 0, 0, 2, which is 7, 10, 15 plus 0 is 15, and 15 plus 2 is, 20 plus 2 is 22. And if we look at the two answers that we've got there, we've now got that A squared is exactly the same thing as 5a plus 2i. So if we move on to the next page now, we are now asked to use the result in part A to show that A cubed must be the same thing as lambda a plus mu I. Well, we know that a squared is 5a plus 2i. So a cubed is a times a squared. So that's the same thing as a times by 5a plus 2i. So that is 5a squared plus 2ai. Now we know that a squared is 5a plus 2i, so that is 5 lots of 5a plus 2i plus 2ai. Now a times I is just a, so 2ai is just 2a. So we're ending up with 25a plus 10i plus another 2a. So that is 27a plus 10i. Now, if you want to have a look at the mark scheme for this question, there are 2 marks for working out a squared at the beginning of the question, and then 2 marks for checking that that was indeed the same thing as 5a plus 2i. And then for the second part of the question, we needed to make use of the fact that a cubed was the same thing as a times a squared, which obtained us the first mark. Replacing the a squared by 5a plus 2i gave us the second mark, and ending up with the answer of 27a plus 10i gave us the answer mark. Our second example comes from the January 2010 paper. We're given 2 matrices, and the first job we've got to do is find the inverse of A. So to find the inverse of a matrix, it's a good idea to start by finding the determinant of the matrix. So the determinant of A is 7 times 2, take away 5 times 3, which is 14, take away 15, so that's minus 1. The inverse of A then is 1 over the determinant times by the matrix obtained by swapping the 2 entries on the leading diagonal, so the 2 and the 7 switch places, and then changing the sign of the 2 entries on the second diagonal, so that's minus 5 and minus 3. 1 over minus 1 is just minus 1, times by 2 minus 5 minus 3, 7. So we're ending up with the inverse matrix being minus 2, 5, 3, minus 7. Now for the second part, we've got to solve the equation a times x equals b. And what we need to do is we need to try and move that a from the left-hand side of the equation across to the right-hand side of the equation by doing the same thing to each side of the equation. So we've got to try and knock out that a. And the way to knock out the a is to multiply each side of the equation on the left by a inverse. So we've got a inverse ax must equal a inverse times b. Now a inverse times a is just the identity, so that's the identity times x equals a inverse times b. In other words, I times x, the identity times anything is just the anything, so I times x is just x, is equal to a inverse times b. A inverse is minus 2, 5, 3, minus 7, times by B, 1, 2, 3, 4. And if we now do the multiplication out for the top left entry, we've got minus 2 times 1 plus 5 times 3. So that's minus 2 plus 15, which is 13. For the top right entry, we've got minus 2 times 2, which is minus 4, plus 5 times 4, which is 20. So minus 4 plus 20 is 16. Bottom left, we've got 3 times 1 is 3, plus minus 7 times 3 is minus 21. So that's going to be minus 18. And then finally we've got 3 times 2, which is 6, together with minus 7 times 4, which is minus 28. So that gives me minus 22 for the value of the matrix X. Looking at the mark scheme, 1 mark for finding the determinant of A, and then 2 marks for carrying that through to the inverse of A. And for part B, first mark is for realising that AX equals B leads us through to X equals A inverse times B, and then we need to use the answer for A inverse and multiply that through by B to obtain the answer and the final 2 marks. Our final example comes from the January 2012 paper and is going to be considering 3x3 matrices. To show that the matrix is non-singular, you have to remember, of course, what non-singular means. A singular matrix is a matrix whose determinant is 0. A non-singular matrix is a matrix whose determinant is not 0. So what we're being asked to show is that the determinant of this matrix is always non-zero. So we need to work out the determinant of the matrix. So the determinant of A is the determinant of the matrix K1, 1, K4, 0, 1, 1. And in order to work this determinant out, what I like to do is I write down the first 2 rows again underneath, and then start working out the products of the diagonals. So the first diagonal I've got is k times 1, which is k squared. The next diagonal that I've got is 1 times 1 times 6, so that is 6. And the last diagonal I've got is 0 times 1 times 4, which is 0. And then I do the same with the diagonals going in the opposite direction. So I've got, first of all, 6 times k times 0, which is 0. I've got 4 times 1 times k, which is 4k. And I've got 1 times 1 times 1, which is 1. So the value of the determinant is k squared plus 6. Take away 4k, take away 1. So that is k squared minus 4k plus 5. And if you write that in completed square format, we have got k minus 2 squared, take away 4, add 5, so that is k minus 2 squared, add 1. And that makes it quite clear that the value of the determinant is always a number which is 1 or more. So the value of the determinant can never be 0. So the matrix is non-singular, whatever the value of k. Right, so they're now asking us to put k equal to 3. And we're being asked first of all to find the adjugate matrix of A, which is sometimes called the adjoint matrix of A. To do that, the major step, and the one that's going to require all the working, is actually to find what the preliminary to the adjugate, which is the cofactor matrix. And to find the cofactor matrix, we start off with this grid of pluses and minuses, and we go along element by element in that initial grid, and we cross out the corresponding row and the corresponding column, work out the determinant of what's left over. So in this case, 3 times 1 take away 4 times 1 is minus 1. And then the entry on the cofactor matrix that we make is, in this case, the same sign as the determinant. So the entry is going to be minus 1. So we now move to the second entry in the cofactor matrix. Again, we cross out the row and we cross out the column corresponding to this entry in the original matrix. We now calculate the determinant of what's left. So that's 1 times 1, take away 4 times 0. So that is 1. And in this case, the entry that we've got circled is a minus, so we've got to change the sign of this determinant. So the entry we're going to make is minus 1. Moving on to the next entry, cross out the row, cross out the column, value of the remaining determinant is 1. We've got a positive there, so the entry is going to stay the same sign as the determinant, so the entry is going to be 1. Moving on to the next entry, cross out the row, cross out the column for this entry. The value of the determinant is 1 times 1, take away 6 times 1, which is negative 5. We've got a minus in the cofactor matrix at the moment, so that means we've got to change the sign of the determinant. So that's going to become plus 5 as the entry. So there's the progress we've made so far. Next entry we're going to have to do is the one in the middle of the matrix. Cross out the row, cross out the column. Determinant of what's left is 3. The entry at the moment is a positive one, so the entry is going to be the same as the determinant, so the entry is going to be 3. Move on to the next one. Value of the determinant is 3. The entry at the moment in the cofactor matrix is a minus, so the entry you're going to have to do is the negative. We've got to change the sign of the determinant, so it's going to be minus 3 as the entry. Same again now for bottom left hand corner. 1 times 4 is, take away 3 times 6 is minus 14. The entry at the moment is positive, so we keep the sign of the determinant as it is, so the entry is going to be minus 14. Now, for the penultimate entry, we've got the determinant is 3 times 4, take away 6 times 1, which is 6. The entry at the moment is a minus, so we've got to change the sign of the determinant to get an entry of minus 6. And then the final entry, the value of the determinant is 8. The entry at the moment is a positive, so we keep the sign of the determinant. So the sign of the entry will be 8. So the cofactor matrix there is minus 1, minus 1, 1, 5, 3, minus 3, minus 14, minus 6, 8. The adjoint matrix is simply the transpose of the cofactor matrix. So the first row of the cofactor matrix becomes the first column of the adjugate matrix. The second row of the cofactor matrix becomes the second column of the adjugate matrix, and the third row the cofactor matrix becomes the third column of the adjoint matrix. Now, we've got to this stage in the question. Finishing it off, finding the inverse matrix of A is now fairly quick. We know that if k equals 3, the determinant of A must be 3 minus 2 squared plus 1, which gives me 2. So the determinant of A is 2, and we know that the inverse matrix is 1 over the determinant times the adjoint matrix, so that gives me 1 over 2 times by the adjoint matrix. Finally, let's just review the mark scheme for this question. For part A, there are 2 marks for obtaining a correct expression for the determinant of the matrix, and then 2 more marks for explaining why the determinant was therefore non-singular. For part B, there were 2 marks for obtaining the cofactor matrix, and then a 3rd mark for obtaining the adjoint matrix, and then moving on to finding the inverse matrix, there were 2 marks available for that. First one for using the determinant, and the second one for linking it to the adjoint matrix.